Okay, this is a pretty common problem. This is number 26. It says at Zion National Park, a loud shout produces an echo 1.8 seconds later from a colorful sandstone cliff. So here you are, and you shout all the way across, and your sound travels over to the cliff, but you have to remember that then the echo comes back. So the distance we're looking at here is d and also d coming back. So really our entire distance is 2d. Remember that velocity is equal to the distance divided by time, and we want to solve this for distance, so we're going to say distance is equal to velocity times time, where the velocity is really the velocity of speed. But remember, because we're dealing with two distances here, we're going to say that that's time for it to travel is actually the time all the way down and back. So we're going to do 2 times the distance is equal to the speed of sound times the total time that sound has to travel. At this point, we can just say d is equal to the speed of sound, which is 340, times the time it travels, which is 1.8, and then we have to divide that by 2 because we need to divide both sides by 2. When you go through and try to solve that, you should end up with an answer close to about 310 meters. And so that's number 26. Pretty common problem. Lots of people miss it because they forget to do the 2 for the distance because they just assume it's going here instead of going there and coming back. For the next problem, we're looking at number 29, and they tell us that a sound wave in air has a frequency of 425. So the first thing they want us to do is find out what is its wavelength. And remember, the speed of sound should be equal to the wavelength times the frequency. So if we want wavelength, we can rearrange this equation very easily and just say it's the speed divided by the frequency. The speed of sound is about 340 meters per second, and we know that our frequency is about 425. If you divide those two, you should end up with somewhere around 0.81 meters. So that's a pretty long wavelength. It says if the frequency of the sound is increased, does its wavelength increase, decrease, or stay the same? For this one, it should decrease. Okay, so it should decrease if the frequency is increased. So we know that because wavelength is equal to speed over frequency. So if the frequency goes up, we know that the wavelength has to go down. Typically on AP tests, they ask you to do this, so you want to make sure that you're as thorough as you can be with the time that you have. Now they want you to calculate the wavelength for a sound with a frequency of 475 hertz. So the same thing, wavelength is equal to the speed of sound over the frequency, and so that would be 340 divided by 475, and that will give you the answer of 0.722 meters. And notice that our frequency from here to here did go up, and so our wavelength had to go down, had to get a little bit shorter as we went through. The last problem we're going to do just in this session is number 30, and it's a little bit more involved. It says when you drop a rock into a well, you hear a splash 1.5 seconds later. So if we have a really deep well and you drop a rock down into that well, it takes a while for that rock to fall and hit the bottom. But once it does, the speed of the sound comes back very quickly. So the time for it to fall is really long, and the time for the echo to come back is really pretty quick. And that kind of makes this problem a little bit more difficult. So to do this one, we need to do 2 equations. The first one's going to be the time to fall. And we know the time to fall should be just related to the equation dy is equal to 1/2 gt squared. So if we solve this equation for TF, we should get the square root of 2 times d, and we won't put the y in, and we're going to divide that by gravity. The other time that we need is the time for the sound to come back up. So let's actually change this to TS for the time of the sound. And that's really simple. That's just equal to the distance that it travels divided by the velocity of the sound, because we know the velocity of the sound should be equal to the distance the sound travels divided by the time that it takes for that sound to travel. We're going to use both of these equations to set up one equation. We know that the total time should be equal to the time to fall plus the time for that sound to get to the bottom. So that's really equal to the square root of 2 times d over g plus distance over the speed of sound. At this point, we're going to just use t. So instead of using these two, we're going to make that t. So this thing right here becomes just t, because that's our total time, and that's the only thing that they've really given us. So our total time here is equal to the square root of 2 times d over g plus d over vs. I find it a little bit easier when I do this problem to go through and go ahead and put all the numbers in and then go through and solve it. So our time here is 1.5 seconds. That's equal to the square root of 2 times d over 10 plus the distance divided by the speed of sound, which is about 340. Now our problem here is we've got a d under a square root and we have a d here. So let's go ahead and rearrange this equation. We're going to set it equal to 0. And we're going to say this is equal to the square root of 2 times d over 10 plus d over 340 minus 1.5. Now, if you're really good, you'll notice that we probably need to make a quadratic equation out of this. And I know that that's probably not a real popular thing to do, but let's go ahead and do it anyway. Let's go ahead and just square this whole thing. If we square the whole thing and rearrange it, we're going to say 0 is equal to d squared over 340 squared plus, now we can get rid of the radical here. So we have d, 2d over 10, and then we're going to subtract from that 1.5 squared. So let's do a little bit of math. 0 here is equal to d squared over, and then 340 squared is 115,600 plus, and then we've got 2d over 10, and 1.5 squared is 2.25. Let's go ahead and multiply each one of these terms times 115,600. If we do that, we can get the d squared all by itself. So that's d squared plus, now we're going to multiply the 115,600 by 2 and then divide by 10. So we get 231,020. So we're going to get 23,120 because we divided that number by 10 times d. And then 2.25 times that is 260,100. Just seems really crazy, but it works out. You can use the quadratic formula, or I use the solver in my calculator to do this. So if you need help using the solver in your calculator, as long as you have like a TI-84, TI-85, TI-86, or TI-89, the TI Inspires also do this. They all have a solver, and that will help you. So if you need that help, come see me and I can do that for you. But in the end, you should end up with a distance equal to 11.2 meters. So that's a pretty big problem. If the depth of the well were doubled, they want to know would the time required to hear the splash be greater than, less than, or equal to 3 seconds. It actually would be less than that 3 seconds, and that's because although the sound travel time would double, the fall time would less than double. And it's because of what you would hear. Okay, it's about 2.1 seconds. So if you would double that 11.2 and make it, somewhere around 21 or so, you would get about 2.1 seconds. And that is the end of the next set of problems.